Dear friends, welcome in the mathematics class. Today we have to see very important theoretical questions on linear differential equations of second and higher order. See the first question. If capital D is equal to d by dx and f of d square is a polynomial in d square with constant coefficients and f of minus a square not equal to 0, then show that first 1 upon f of d square cos of ax plus b is equal to cos of ax plus b upon f of minus a square, and second 1 upon f of d square sin of ax plus b is equal to sin of ax plus b upon f of minus a square. Means instead of d square we have to put minus of a square, but condition is that f of minus a square not equal to 0. Now you have to see the proof. Consider derivative of cos of ax plus b. D means d by dx, so take out derivative of cos of ax plus b. So that derivative is minus of sin of ax plus b into derivative of ax plus b, which is a, and so derivative of cos of ax plus b is equal to minus a sin of ax plus b. Again operate d on both sides, so means take derivative with respect to x on both sides. So we get d of d cos of ax plus b is equal to d into the bracket minus a sin of ax plus b. D into d, it is d square, so you can write this is d square cos of ax plus b is equal to, now we have to take derivative of this square bracket. Here we observe that minus a is constant, so take that minus a outside of that derivative, and so we require here derivative of sin of ax plus b, which is cos of ax plus b into a, and therefore d square cos of ax plus b is equal to this minus sign as it is a into a, it is a square cos of ax plus b. Now again operate d on both sides, so we get d into d square of cos of ax plus b is equal to d of minus of a square cos of ax plus b. D into d square, it is d cube cos of ax plus b is equal to, now you require derivative of this square bracket. Here minus a square constant, so take outside of that, so we get derivative of cos of ax plus b. Now find out derivative of cos of ax plus b, which is minus sin of ax plus b into a, means it is minus a into sin of ax plus b. So this minus a sin of ax plus b, and therefore d cube cos of ax plus b is equal to minus a square into minus a sin of ax plus b. Again operate d on both sides, and so we get d into d cube cos of ax plus b is equal to d of minus a square into minus a into sin of ax plus b. So this will become d raised to 4 cos of ax plus b is equal to minus a square is constant, minus a also constant, take outside of that one, and so remaining derivative of sin of ax plus b. Now find out here derivative of sin of ax plus b, which is cos of ax plus b into a, and so we get d raised to 4 cos of ax plus b is equal to minus a square minus a cos of ax plus b into a minus a into a, this term will become minus of a square, and so we get d raised to 4 cos of ax plus b is equal to minus a square into minus a square cos of ax plus b. Now observe this equation, d square cos of ax plus b is equal to minus of a square cos of ax plus b. We can write this equation as d square raised to 1 cos of ax plus b is equal to minus a square raised to 1 cos of ax plus b. So we rewrite this equation as d square bracket raised to 1 cos of ax plus b minus of a square bracket raised to 1 cos of ax plus b. Denote this is equation number 1. Similarly, we can write this d raised to 4 as d square bracket square, and this minus of a square into minus of a square, it is minus of a square bracket square. And so we get a d square bracket square cos of ax plus b equal to minus a square into minus a square, it is minus a square bracket square cos of ax plus b. Denote this is equation number 2. Now observe equations 1 and 2. Here is d square raised to 1 and here is d square raised to 2. Cos of x plus b, cos of ax plus b, and in the right hand side here is minus a square bracket raised to 1, here is minus a square bracket raised to 2 cos of ax plus b. If we continue to find derivative, we get d square raised to r cos of ax plus b is equal to minus a square bracket raised to r cos of ax plus b. If we continue this process, we get d square raised to r cos of ax plus b is equal to minus of a square bracket raised to r cos of ax plus b. Now here observe that d square raised to r means this is function of d square, and minus a square bracket raised to r means this is function of minus a square. This is polynomial in d square, this is polynomial in minus a square. So you can write f of d square cos of ax plus b is equal to f of minus a square cos of ax plus b. F of d square is a polynomial in d square with constant coefficients. And so transfer this 1 up f of d square to the right hand side, and so we get cos of ax plus b is equal to 1 upon f of d square into f of minus a square into cos of ax plus b. Here 1 upon f of d square means this operator represent the integration, and here a is constant, so a square minus a square is constant, so f of minus a square is constant. So take this constant outside of that integral, and so we get cos of ax plus b is equal to f of minus a square into 1 upon f of d square cos of ax plus b. Here you know f of minus a square is not 0. This is given in the question. As f of minus a square is not 0, we can transfer this term to the left hand side, and so we get cos of ax plus b upon f of minus a square is equal to 1 upon f of d square cos of ax plus b. Now interchange right hand and left hand sides, so we get 1 upon f of d square cos of ax plus b is equal to cos of ax plus b upon f of minus a square. Hence the proof of the first part. On the same line we can prove the second part also, and so similarly we get 1 upon f of d square sin of ax plus b is equal to sin of ax plus b upon f of minus a square. Means for finding integrating factor where there is a term of d square, we can put d square is equal to minus a square. But condition is that f of minus a square should be not 0. So this is the proof of that result. Now see the second question. If capital D is equal to d by dx and f of d is polynomial in d with constant coefficients, then show that 1 upon f of d e raised to x into v is equal to e raised to x into 1 upon f of d plus a v, where v is a function of x. Now we have to see the proof of this result. Consider here u function of x. Now take derivative of e raised to x into u. D means d by dx, so d by dx of e raised to x into u. Now use here u into v formula. Say this is first function, this is second function, and so first derivative of u, v as it is, and then plus u as it is, derivative of v, and therefore d of e raised to x into u is equal to e raised to x du, first term as it is. Now here we have to find derivative of e raised to x, which is e raised to x into derivative of x, which is a. So that derivative is u into e raised to x into a. And so this is equal to e raised to x du plus, take this a as a coefficient, so a u e raised to x. Now we observe that both the term contains e raised to ax and u also, and so we get d of e raised to x u is equal to e raised to x common to the left hand side and u common to the right hand side, so we get this is equal to e raised to x d plus a u. Now denote this is equation number 1. Again differentiate on both sides, means again operate d on both sides, so we get d of d e raised to x u is equal to d of this bracket e raised to x into d plus a into u. Take this d inside one, so we get d square e raised to x u is equal to, now we have to find derivative of this term. So see, this is the first term, e raised to x is the first term and d plus a into u the second term. See, this is u and this is v. So first derivative of u, v as it is, then plus u as it is, means d plus a into u as it is, derivative of v means derivative of e raised to x, which is a e raised to ax. So we use here u into v formula, and so this is equal to e raised to x. Observe this equation, e raised to x take out e raised to x common in right hand side and d plus left hand side and d plus a into u to the right hand side. So we get this is equal to e raised to x into the bracket d plus a into the bracket d plus a into u. Now this term will become d plus a bracket square. And so we get d square e raised to x into u is equal to e raised to x as it is d plus a bracket square into u. Denote this as equation number 2. Now here observe these two equations, equation number 1 and equation number 2. In equation number 1, we can write this as d raised to 1 e raised to x u is equal to e raised to x d plus a bracket raised to u. In the left hand side there is d, and in the right hand side in the middle term there is d plus a. Similarly, in equation number 2, a is a square. D square e raised to x into u is equal to outside e raised to x in the middle term d plus a bracket square into u. Now continuing in this way, we get d raised to k e raised to u e raised to x into u is equal to e raised to x into d plus a bracket raised to k u. We generalize this equation 1 and equation 2. Now see this d raised to k means this is the function of d, that is the polynomial in terms of d. And here d plus a, it is the function of d plus a. So you can write d raised to k as f of d and d plus a bracket raised to k as f of d plus a. And so we get f of d e raised to x into u is equal to e raised to ax as it is f of d plus a into u. Give this is equation number 3. Now take here d plus a is equal to u. Put this value as u. So d plus f of d plus a into u is equal to v. See this value as v. That is u is equal to 1 upon f of d plus a into v. And now put this in equation number 3. And so we get f of d e raised to x into value of u, which is 1 upon f of d plus a into v, is equal to this e raised to x as it is, and f of d plus a into u is equal to v. So we get like this. Now operate 1 upon f of d on both sides. So here we get 1 upon f of d e raised to x into 1 upon f of d plus a into v is equal to 1 upon f of d e raised to x into v. Here f of d get cancelled. So we get e raised to x into 1 upon f of d plus a into v is equal to 1 upon f of d into e raised to x into v. Now interchange is the right hand side and left hand side. So we get 1 upon f of d e raised to x into v is equal to e raised to x into 1 upon f of d plus a into v, where v is a function of x. As u is function of x, so v is again function of x. And so we get the required result 1 upon f of d e raised to x into v is equal to e raised to x into 1 upon f of d plus a into v. So this is the proof of that important result. Now move to the last result, last question. If d is equal to d by dx and f of d is polynomial in capital D with constant coefficients, then show that 1 upon f of d xv is equal to square bracket x minus 1 upon f of d into f dash d square bracket complete 1 upon f of d into v. Here f dash d means derivative of f of d. See the proof. Let u be any function of x. By Leibniz theorem, we know nth derivative of u into v is equal to nth derivative of u, v as it is, plus nc1, n minus 1 derivative of u, v1, plus nc2, n minus 2 derivative of u, v2, and continue like this. So similarly, if we instead of v, we put x, then nth derivative of u into x is equal to nth derivative of u, v means x as it is, plus nc1 means it is n minus 1 derivative of u means d raised to n minus 1 into u, then first derivative of v means first derivative of x, which is 1, and in next term you require second derivative, third derivative, continue in this way of x, but second derivative, third derivative, all of x all are 0, And so d raised to n ux is equal to d raised to n u into x plus n d raised to n minus 1 u into 1. So you can write this as d raised to n xu is equal to x d raised to n u plus n d raised to n minus 1 u. So this is the nth derivative of this product. Instead of n, we can put k. So we get d raised to k xu is equal to x d raised to k u plus k d raised to k minus 1 u. And this is as equation number 1. In question, f of d is polynomial in d with constant coefficient. This is given. So f of d is polynomial in d means f of d is equal to d raised to n plus p1 d raised to n minus 1 plus p2 d raised to n minus 2 plus dash 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 pn minus 1d plus pn. Here p1, p2, p3, pn all are constants. Treating d as a variable and differentiating equation second with respect to d, we get, now we have to differentiate this equation second with respect to d. And so we get f dash of d is equal to derivative of d raised to n with respect to d. It is n d raised to n minus 1. Then derivative of p1 d raised to n minus 1. Here p1 is constant, so it is as it is. Derivative of d raised to n minus 1 is n minus 1 into d raised to n minus 1 means n minus 1 into d raised to n minus 2. And similarly, we can find derivative of p2 d raised to n minus 2 and continue in this way. In last but one term, pn minus 1 constant and derivative of d with respect to d is 1. And in the last term, pn, which is a constant, and derivative of constant is 0. So in last term, we get here 0. So this is the f dash d. Now, f of d into x into u is equal to, now we have to find this value, f of d into x into u. You know f of d, put that value here. This is the f of d polynomial in d, which is d raised to n plus p1 d raised to n minus 1 plus p2 d raised to n minus 2 plus dash 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 pn bracket complete x into u. Take this xu inside 1. So we get d raised to n xu plus p1 d raised to n minus 1 into xu plus p2 d raised to n minus 2 into xu plus dash 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 pn into xu. Now find out the nth derivative by using Leibniz theorem, which we will find in equation number 1. See equation number 1, d raised to k xu is equal to x d raised to ku plus k d raised to k minus 1 u. Now see the first term. In first term, we required here nth derivative of xu. So instead of k, put n. So we get d raised to n xu plus p1 d raised to n minus 1 xu. Now we have to find derivative of the second term, nth derivative of n minus 1 derivative of xu. So instead of k, put n minus 1. So we get this term and continue like this. Now observe this equation. First term, third term, fifth term, that is odd term, contain x. So collect all that terms and take out that x as a common. So in first term, we get d raised to n. Take out u common in the right hand side and x common in the left hand side. So in first term, we get d raised to n. In third term, we get p1 d raised to n minus 1. In fifth term, we get p2 d raised to n minus 2. Continue like this. In last term, we get pn u, and that u outside. Plus, now see the remaining term, that is the even terms. We can take u as a common to the right hand side, and so we get n d raised to n minus 1. Here n d raised to n minus 1. Here n minus 1 p1 d raised to n minus 2. Then n minus 2 p2 d raised to n minus 3, and continue in this way. In last but one term, we get pn minus 1 and that u outside. And therefore f of d into xu is equal to this x as it is. Now see these two equations, equation number 2 and equation number 3. d raised to n plus p1 d raised to n minus 1 plus p2 d raised to n minus 2 plus dash 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 pn is the value of f of d by using equation number 2. So see this square bracket, this represent f of d, and this another square bracket represent f dash of d by using equation number 3. This is the f dash d and this is f of d. And so we get f of d into xu is equal to x into f of d into u plus f dash d into u. This is equation number 4. Now write down this equation again. Equation number 4, which is f of d into xu equal to x f of du plus f dash du. This is that equation. Take here u is equal to 1 upon f of d into v, where u is function of x. And so we get, by equation 4, we have f of d x value of u, which is 1 upon f of dv, is equal to x f of d value of u 1 upon f of d into v plus f dash of d, and then value of u again 1 upon f of dv. And therefore f of dx into 1 upon f of dv v is equal to, here f of d get cancelled, so remaining x into v plus f dash d upon 1 upon f of dv. Transfer this f dash d upon 1 upon f of d into v to the left hand side, so we get f of dx into 1 upon f of dv minus f dash of d into 1 upon f of dv is equal to this xv as it is. Now interchange right hand side and left hand side, so we get xv is equal to f of d into x into 1 upon f of d into v minus f dash of d into 1 upon f of d into v. Now operating 1 upon f of d on both sides. Take 1 upon f of d on both sides. So we get 1 upon f of d xv is equal to 1 upon f of d in first term as well as in second term. So we get like this. Now observe that here this f of d get cancelled. So 1 upon f of d xv is equal to x into 1 upon f of d into v minus 1 upon f of d into f dash of d into 1 upon f of d into v. And therefore 1 upon f of 1 upon f of d into xv is equal to, see this term here, 1 upon f of d into v and 1 upon f of d into v is common, so take that common outside, and so we get 1 upon f of d xv is equal to x minus 1 upon f of d into f dash of d into 1 upon f of d into v. That's our result, hence proved. So dear friends, stay home, save lives, take care. Thank you.